Oh, perfect. Um, okay. And thank you all for coming for random sample today. Today I'm really excited to have Qizheng from Stanford to join us to present his latest work on agentic content engineering. So I met Qizheng last year, workshop at Stanford, and at that time both of us were working on keeping cache optimization, like more for infrastructure stuff. And then like half a year after, I realized someone from our internally run sample channel, they posted an interesting paper on agent stuff. And I checked the paper and realized it was written in Qizheng. And then a few weeks ago, I sent him a message. And then I realized he has done a lot of work on this domain. So I'm really excited today to hear him talking about his latest research. But before, let me give you guys a quick introduction of Qizheng. So he's a final year PhD student at Stanford. Before that, he finished his undergrad from University of Chicago. He has done a lot of amazing work on both KV cache stuff, infrastructure, and nowadays on agent. I think now his main research interests are more focusing on building agent or AI system that can continuously learn from experience. And he got a lot of awards which recognize his work. I'm just going to read some of them. So his work has been recognized by Eurosys Best Paper Award and also an SRC Jump 2.0 Best Paper Award, and also an ISCE Distinguished Artifact Award. So again, really excited today. I guess without further ado, Qizheng, please take it away.
On the premise of interrupting again, actually, Qizheng, there's a very interesting connection. I was going through your page. When I was a PhD student, I don't know, like 8 years ago, I wrote my very first paper with James. I just saw that you've been working with him. Yeah, and I don't even know, like it was 10 years ago. And then I met him at Generative this year after 10 years. And we actually discussed this paper. So it's good to see you here presenting it.
Oh yeah, cool. Yeah, I think he has a lot of very good ideas for and he gave a lot of very good advice for this specific work. So yeah, and I'm happy to talk more about that later. But I think I'll get started first then. So this talk will be 40 minutes. If you have any question, you can also ask it at the end, or feel free to interrupt me at any time if you have any thing you want me to clarify in the middle. Yeah. So this work is more on the machine learning side, but I will talk about some of the very interesting connection this work has with other directions. For example, if you work on the system side or if you work on serving side, I do think this work has very interesting connection as well, which I will make in the middle of this talk as well. Yeah. So this paper is about the idea of context evolution. So after hearing this talk, you'll learn about why I personally feel that context evolution is an underappreciated topic, and why I believe it's exciting for both researchers and people working in industry. Yeah, and this will be appearing at iClear this year. So, and this is trying to work with my co-authors at Stanford, Villanova, and UC Berkeley. Yeah, so we get started with something the group has been doing since last year, which we had been looking at coding agents. In particular, coding agents that use tools. If you can think of things like Cloud Code or maybe Codex, these are very similar examples. But here I will be using an example from a benchmark called AppWorld, which features a collection of different apps like Spotify, Gmail, Venmo, etc. And the benchmark requires a coding agent to interact with these apps in an environment by writing code. For example, writing code to finish tasks that is long horizon and multi-turn. So most of the tasks in this benchmark are more than 10 turns and has a lot of tokens in the entire trajectory. So these are very multi-turn and long context tasks. Yeah, and the requirement here is that the agent must use tools and APIs given by the benchmark to solve these problems. So a lot of the pre-trained knowledge would not help in terms of solving these agentic tasks. One example we give here is to list some songs from a user's Spotify playlist, which requires logging into the user's Spotify account using the API provided, and then to list the song information there. So some of the example we have here, this is a list of not a comprehensive one. We show some example API or function calls given by the benchmark. So the coding agent can use these to access the playlist and show all the songs from the users. So one typical problem we observe is that the agent often forgets to retrieve a user's access token before further operations. As an example here, we list a piece of code, but you don't have to understand everything here. The major problem here is that on the first line, the agent assumes that we have the access token already saved in some existing variable and try to access that. But this will give you a key error because the access token has never been saved from the user. So basically, there's no authentication step before we access the user's playlist on Spotify. So I was thinking maybe we can just have a very simple fix by letting the language agent know that you have to go through the login process to get the access code to finish authentication before you do anything on a user account. So I just say that let's manually enforce that in the context by having a principle. Let's say principle 1 is always log in to retrieve your access token from the user as a first step before you do anything else on this specific app. So this works because this, in particular, we ask the agent to do something very specifically, very explicitly in a prompt. So the agent would actually go and just say, I'll just log in first to get the access token. So with this specific contextual guidance, the agent can fix some of the I would say these are very small errors it goes through. And most importantly, this is not a mistake due to a lack of factual knowledge, like things you see on Wikipedia that is missing in agents, for example, pre-trained weights. That is not the case. In many cases, we find that agents are missing contextual or procedural knowledge. In the case of coding agents, it could be it's missing information about a user's specific file, or it's missing information about how one specific action should be achieved, or one specific test time action can be done, how the sequence should be. So in many cases, we realize that a lot of these are due to this kind of failure, not a failure you typically see in the pre-training and post-training stage of models due to, for example, missing of facts or missing of like some specific tool using capability and so on. So we want to take a look at whether we have some existing approaches that can solve this. So I'm going to compare some existing adaptation paradigms for agents and for language models in general, and I want to highlight some thoughts on why existing approaches are not the best fit for these problems. So the first approach, if you work on the typical model development process, involves everything from pre-training, mid-training to post-training, everything related to weight updates. So we take some training set and we post-train the model, or we mid-train the model so they have some specific knowledge or capability. The good thing is that this is very standardized process used in industry, and it's providing very strong and compact performance at inference. But it is also pretty slow, requiring a lot of infra efforts and hard to audit and roll back if you want a very strong performance or test time adaptation behaviors. Another one used a lot in industry is retrieval augmented generation, or anything generally related to in-context learning. So this usually takes a vector database, and we search for things that are semantically related during inference, and then we inject that as external knowledge during inference. So the good thing about this is we have external knowledge that you can always use during inference. But the bad thing is, emergently, we find that this is usually good for retrieving knowledge that are already existing in your database. But if you have things that you accumulate during test time, let's say for a procedural knowledge, contextual knowledge, tool protocols, and like how-to knowledge that are not explicitly stored, then it's not possible to retrieve them explicitly from some existing database. So you want some way to accumulate these knowledge yourself at the same time. And at the same time, we realized that both approaches we listed here are actually developed quite a few years ago. So if you look at the trend, like how things are going on in the most recent like 2 to 3 years, a big trend here is that frontier models are getting much better at long context capabilities. And unfortunately, most of the existing approaches are not actively leveraging this growing capability of frontier models. So here I list out a third-party figure from some AI analysis website. And you can see that on the y-axis, we have the number of tokens, and x-axis is a timeline. I was very surprised that April 2023 was already almost 3 years ago. But I do feel like it's almost like a decade ago if you work in this field, because things are happening so fast. So only 3 years ago, we have like a context window of 10,000 tokens. But now we have over 1 million. So things are growing really fast. I would even call this a new kind of scaling law for context window input. And if you look at the complete work of Shakespeare, that's only 1.2 million context. So you can fit in really a lot of things in these context window for frontier models. Another thing, if you look at the orange dots, is that the models are also better at proactively using information in the long context. So the orange dots are, if you want to reach 80% performance on needle in a haystack style benchmarks to retrieve like information from very large context, what is the context window you can guarantee to reach 80% accuracy? So this is also increasing every year, which tells us that we're having much stronger long context capability. So we just wonder, is there a way we can develop a learning paradigm to proactively leverage this? And if you look at X, like people are already thinking of this, like from industry, people are developing methods not just for prompt engineering, but also for context evolution in general. So continuously optimizing context and in general to make them better. So this talk is about context evolution and how to make them. And we'll talk about how we formalize context evolution as a system problem in general. And this enables much better test time learning, interpretable outcome, and also model agnostic performance. So you can always benefit from latest model release with your method. Yeah, and I'll talk about the problems as well on the next few slides. So we start with some analysis of some existing approaches, and we find that so if existing approaches are good enough, like if we find very good prompt optimizer can solve all the problem, then we don't have to develop new things. But otherwise, like we did some failure analysis for existing approaches. So we take two major classes of approaches right now. One class of approach is very good prompt optimizers. Another class are working agent memory. So if you work on things in agent memory, these are updating agent context during online scenario. So we analyze both these methods, and we brief like the scenario like this. So you start with some existing context, no matter if it's a prompt or some online memory. And then you go for some new query or new task, which gives you some new generation. And what happens right now a lot in the community is that people would take another language model or agent, use that as the reflector to give you reflection in the form of natural language, so natural language feedback. And it tells you explicitly like what you need more in the context, like maybe you missed some very useful hint or principle in general. And that becomes your next context or next version of your memory. And eventually, like you select the best version of context or memory, maybe using some validation set or other optimization objective. So we realized that this approach actually suffers from two particular issues. So the first one is that a lot of these paradigms are actually modeled after a human expectation of how we want the prompt to be. So we call the first problem brevity bias, that in many cases, because human prefers like a concise and generic instructions for a task. We also project the same expectation when we are doing a context optimization for agents. So there's always a preference, in many cases, preference for short and concise instructions. And another issue is we observe that empirically, information can get lost over time, especially for multi-turn and long horizon tasks. For example, in the case of dynamic cheat sheet, we find that we start with an empty context. So we do a lot of adaptation over time for multiple adaptation steps. So at step number 60 here, we have 18,000 tokens in the context. And then, but suddenly, next step, it's being rewritten into a very short and concise summary of what the context contains, instead of preserving all the details, which we call a context collapse. So more than just the behavior we show here, which happens suddenly, which is easier to prevent, we also empirically see a lot of the cases when many times the information is lost silently over time. So even though the number of tokens is like stable or growing, but some of the important knowledge points are degraded or rewritten over time, just without humans being notified, which is even more scary if you want to use this kind of context update mechanism in production, because you don't want to lose wisdom in a second. So we realized that if under the current paradigm, we're modeling context more like a limited resource, and we're trying our best to make it concise or just throw away things that are potentially irrelevant. But our proposal here is that for agents, they're much better at distilling like a relevance or figuring out what is useful. If you follow a related work on like agentic retrieval, many times you want to make a decision based on many contextual information, like for cloud code, your code base, for personal agents, like a user past information in user memory. So we argue that the context should function not as concise summaries, but as a very comprehensive and evolving medium for test time learning that is filled with rich and detailed insights. Yeah. We'll also talk about what happens if your context is full. We'll talk about that in our design as well. Yeah, so we introduce a few recipes to make this happen. So we're going to introduce these recipes one by one. So the first recipe we introduce is a very simple one, which we call incremental context update. So we basically change the paradigm of monolithic rewrite of a context, which happened a lot in previous work in agent memory or prompt optimization. We change this to be a new paradigm with incremental update. So instead of having a new generation or a full rewrite of previous context, we always have incremental delta updates at the end, or maybe we just append things to different sections, which will very soon show an example of an example context we generate and how that relates to incremental delta update. This gives us a much stable control of and graceful scaling of context over time, without losing prior information silently or suddenly. Yeah, and actually, I would actually go to instead of going like by order of the slides, I want to show everyone an example of the context we generate to give a better sense of why our design of the context gives you better incremental update and graceful scaling of context. So here we show an example from the same benchmark we introduced on the first slide, the April agent example. So we see here, this is a partial snapshot of the playbook we generate, because the full version is pretty long. So we see that we have two components. The first one is predefined general section names, like strategies, rules you should follow, code that can be reused, and also things like snaps, pitfalls you should avoid. Another component is all these bullet points. We organize insights by bullet points under different sections. And one thing we did not show here is that the bullet points have a metadata field other than the main text field. So the metadata, other than the number we show here for retrieval, we also have metadata containing two counters. One counter is counting how many times the agent finds this insight bullet point to be useful. Another time is how many times the agent finds it to be harmful. So we will mention very soon that these two metadata bullet points will be used for a periodic cleanup of the playbook we showed here. Yeah. So overall, we designed this playbook in a way that we want the context to be cumulative and also to be updated incrementally so that they can gracefully scale out and make sure you preserve all the previous information. Yeah. So these are the designs for our update mechanism and the context. So we want to show the system design as well for how we achieve that. So we put things together into a framework we call Agentic Context Engineering, abbreviated as ACE, which has 3 different components. So I'll very quickly walk through the process here. So first, we start with some new task or new query and some existing playbook. So we start with an empty one. You can give it an empty one, or you give it some predefined section names. So we start with a generator. This generator can be anything ranging from a language model to some agent design. You can go as simple as a React agent, or it can be as complex as a multi-agent system. So this gives you a generation in the form of agent trajectory. So we are going to take all the execution history from an agent, no matter if it's reasoning trace or a tool call history. We take it as trajectory, and we give it to the next component, which is a dedicated reflective in the form of a language model that generates natural language feedback in an iterative fashion to extract the insights. So for example, we explicitly extract what are some reusable strategies or domain knowledge or pitfall we want to avoid from the reflective. And we do that from in many iterations to make sure that we are not ignoring information in just one iteration. And also we want to make sure we do not overfit by looking at different trajectories. Yeah, and that goes to we take that as insights, and that goes to a dedicated context curator, which is only responsible for taking in generated insights and existing playbook, and then do a very simple append to make sure that we are growing things incrementally. So that append is done by not by a language model to make sure that we actually grow things in a deterministic fashion. The curator uses language model to determine, for example, periodically we have a cleanup process. We look at different metadata for different bullet points. For example, we can remove things that are the agent things that are harmful periodically based on a harmful counter. And then we merge things that are semantically similar using a very lightweight language model here to make sure that our playbook is dense and compact over time. So yeah, there is a periodic cleanup process. So the curator would actually generate these delta context updates and update the playbook to be ready for the next iteration. Yeah. So the recipe we have here is we have a structured division of labor to make sure that the responsibility of this update process is not centered on one single language model or one single agent. Because if you're familiar with a few agent development practice, this prevents context pollution for different components and make sure that each model is tasked with one very specific task so that it is able to do it in a very clean and formatted way. So essentially, you can understand this as a multi-setup for a context update. Yeah. So at this point, you might ask, is this just a very fancy prompt engineering, or prompt engineering with a fancy framework? So I would say the answer, in some sense, is yes. But there are 2 things you have to agree right now. The first thing is that if you are working on agents or language models, in fact, probably the only way you update them during test time in a cheap and fast fashion is to update its prompt or context. If you want to incorporate new information or new observation during inference, context update is the most efficient and most effective way you can achieve this kind of test time update. The second thing is that we want some autonomous way to achieve this kind of update. We don't want a human to watch the trajectory all the time and say that, oh, this is going to be the 10 tokens I inject for the next iteration. So it's good to have an autonomous framework so that we don't have to do manual prompt engineering. Yeah. So if you understand these points, or if you agree with me, you don't have to agree with me, but what ACE essentially is that is we formalize context evolution as a system problem. So essentially, ACE is if we put it in a very clean state approach, it is pushing out a state, pushing out context as a state during inference. And we have an update operator during that state. And eventually, what I introduced on the previous slide is an agent loop architecture for making that state and update operator happen in an efficient way. So let me explain that in detail and why that is interesting. So for state, we have a better representation of evolving context. So instead of having a huge blob of like a random text, we have different sections, and each section is composed of itemized bullets with metadata indicating whether this bullet point is helpful or not. So we have a design of the context which is much better for fine-grained retrieval, localization, incremental update, and it's also good for periodic deduplication and removal of harmful contents. So this representation is, in principle, a design that makes evolving context possible. The second thing we have is an update operator, which is delta update and deterministic merge. This ensures that we preserve old knowledge and make sure that the context would scale gracefully without losing old knowledge. It also enables a much more efficient parallel or batched processing for learning new things. So you can have a lot of agents learning in parallel, learning a lot of delta updates, and then merging these delta updates at the same time. So we have a batched version in our open source repo. And finally, the architecture we introduced is essentially an autonomous loop and a structured division of labor, which helps us separates the responsibility across different language models and agents. So this helps avoid context pollution and so on. So some of you might be curious that why do we introduce this kind of architecture? So the short answer here is that the architecture we introduce here is actually a manual design. So you can argue that this is not the optimal design. One follow-up research we are currently exploring is we can, using coding agents to explore meta design for these autonomous architecture for update context. So you don't have to use the same architecture we use, but you can let an agent explore the best meta design empirically. Yeah, that is something we are trying right now. So I'll pause here a little bit in case you have any design-related questions before I go on to evaluations. I see someone raising hand, actually.
So I had a quick question. So when you create the playbook, so as of now, do you just give the entire playbook, or do you have like a way to retrieve relevant parts of it?
So for the paper, we use the full playbook for experiments. But for the open source version and for a lot of the new things we're doing now, we use retrieval, and we're retrieving using bullet points as a smallest unit. But we still preserve the section names. So essentially, you have a subset of the playbook if you want to use retrieval. That's why, like here, I said the representation we have is good for fine-grained retrieval because we also have retrieval support. So you can use any retrieval methods in orthogonal to this framework.
I see. Thanks.
I see. Akash, yeah, please.
Yeah, I just have one question. Maybe I missed it and you already said, and in that case, just like you can point me back to it. But do you allow as part of this context engineering or in general, sort of removing parts of the prior context? And if so, then does that lead to some kind of a I'm just thinking in terms of like the distribution that of the context that the model has become used to, and if you're directly allowing edits or deleting parts of it, does it have any negative impact?
So the short answer is yes, we allow deleting things from the context, and especially if you look at the representation for the context, we do have it's not shown here, but we do have a metadata field which shows you that oh, this is a counter for the number of times the agent find this context to be useful. This is the counter the number of times the agent find this bullet to be harmful. So a naive thing we did is we periodically remove the harmful bullets based on the counter, and we also do periodic merging of semantically duplicate bullet points. But if you're saying active removal, like this is something that human can do, but for now we only remove the harmful bullet points.
Okay.
Yeah, just to be very conservative here, because you don't know, like maybe something can be relevant at some point. Yeah.
And the semantic merging is how do you let the model decide what is semantically similar, or you use something else?
So we use a deterministic framework by looking at the embedding for each bullet point, and then just do a semantics, like a similarity search. Yeah.
Gotcha.
And I want to like just raise one interesting point here. So you might want to ask, like, what would happen if the context just is full? Like, what would happen if the playbook is full? So first, we like I just mentioned, we already supported retrieval in our open source repo. Another thing we believe is the case is you can use ACE along with many inference time methods. Like if you know like the recursive language model paper, you can use ACE along with recursive language model. So we're also trying to support ACE plus RLM in our code base. So you can use a lot of sub-agents to search over your playbook instead of having one model handle everything in your playbook. Or you can do some offloading. Just say that you have just like OpenClaw, you have a long-term memory and you have a lot of subfiles for like full logs and so on. So this is something that I think is going to be some flexible design you can use in the ACE case. The playbook is designing a way for long-term context, but if you have something you want to offload, you can also do that. Maybe not just as form of a context playbook, but also, for example, you can we're exploring generating agent skills as well as a output. You can try that at offloading agent skills. If the current distribution is not using a specific agent skill, you can ignore that from the context and so on. So there are a lot of things we can do here. We were working on this last summer and September. So a lot of things has happened since then. Like so a lot of things you can try based on this architecture and this idea. Yeah. So I want to move on to the evaluation part. So I want to highlight some interesting things on the performance side and on the efficiency side. And I want to like make sure that after you hear about the evaluation part, you feel like it's not just like we're 10% better than prior work. So we take the same use case on AppRoad, but we also have a lot of other benchmarks in finance, in medical, in text to SQL, and we also have some terminal agent, web agent use case in the open source repo. But here I'll just go with the AppRoad case. So we use the React agent as the base agent, and the numbers here are on a range of between 0 to 100. The higher the better. So we first explore the offline case where you optimize the system prompts. So we have two examples. Like Japa is a very good like a system prompt optimizer, and then you have retrieval based in context learning. So we show that you have some gain with like a system prompt or ICL-based approaches because you retrieve some relevant tasks or just distill some relevant knowledge. But because we want a lot of the details from like what we just show in the example playbook, like just telling the model like you should do something in a very detailed way. So these approaches are not as good as ACE in terms of preserving a comprehensive playbook that has all the details you want, and a playbook that is evolving to make sure that you don't just have a one-shot version of it. Yeah, and most excitingly, we find that ACE does not have to use a labeled supervision to generate this playbook. The reason is because we have a very nice coding environment. So we have all the messages like after we write some code, we see whether it's giving some error or it's giving us some follow-up environment feedback. So ACE can directly use these environment feedback for optimizing the playbook. For example, if an API call throws an error, we can extract some insights, say, oh, maybe you make a mistake in some argument name, as an example. So in the case of agent, ACE can actually evolve without label supervision by using code execution and environment feedback. We also study the case of agent memory in online adaptation. Like you start from offline and then you go for online eventually. We find that in the case of online adaptation, ACE is being able to accumulate the details over time better than baselines like dynamic cheat sheet. This is because we observe a lot of context collapse in dynamic cheat sheet, which loses information that are important over time. So that is the case for agent memory for ACE. Yeah. So ACE can evolve both the offline context and online context. So offline context for system prompts, online context for agent memory. And another exciting thing we observe is that we have a better use of tokens and much lower cost and better efficiency in general. So we find that we did a fine-grained component-wise cost analysis for ACE and JAPA, which is the prompt optimizer we mentioned. So we find that during adaptation stage, for adaptation here, I'm referring to offline adaptation for generating the playbook or the context. We find that ACE uses much fewer tokens, both input and output, for the process, because we avoid exhaustive search, and we also avoid a rewriting of or regeneration of previous contents, or like regeneration of the entire context. So we actually use a much fewer, 80% or even more fewer tokens for the adaptation process. And this also leads to much lower latency. So if you look at the latency we have, we are 82% of like faster than like the JAPA exhaustive search approach here. So during adaptation, we find that we reduces token and token use and latency significantly, as for example, very popular prompt optimizer approaches. Yeah. So you might want to ask, like, but the generated context of ACE is much longer than the generated context of ACE or like other approaches. Would that cost you much more during inference because you have a longer context? We also did some analysis and we realized that the generated playbook from ACE is largely, because we use incremental update, so a large part of the content is preserved like unchanged or static during like adaptation. The good thing is that if you have things that are unchanged from previous inference, you can use a KV cache reuse to reduce your cost of long context serving. So as an example here, we did some analysis for the inference stage. We find that ACE uses much more like raw input tokens, almost like 120% more input token because we have longer playbooks. But the good thing is that we actually benefit a lot from existing infrastructure for efficient serving, like a KV cache reuse. So here we use the default prompt caching API from OpenAI API. We find that more than 90% of the playbook tokens can be served from KV cached prompts. And this would reduce like 82% of your input token cost, which is really exciting because this is a point where you develop a new AI technique for continual learning, and it benefits a lot from existing serving infrastructure on KV cache reuse. Yeah. So that is something we believe that longer context does not necessarily translate directly to higher serving cost. So it's not going to be a linearly higher cost. Yeah. And so just to give a summary of the results we have a few benchmarks on agents, on domain-specific tasks, and we are much better on accuracy, application level accuracy on prior work. We're also much more significantly better in adaptation latency and the dollar cost we spend on the process. Yeah. And for inference, we also benefit a lot, even from KV cache reuse, even though the playbook is much longer. So we have a very short summary here. If you're interested in more results, you can always refer to the iClear version of the paper, which is released right now, the camera-ready version. We just released it. We have a lot of additional analysis and additional domains and benchmarks if you're interested in looking at more results. Yeah. So I want to quickly talk about a production use case we have been working on recently with a startup company called AnyShift. So AnyShift has been using agents for doing root cause analysis in cloud and system scenarios, and they have been using ACE since October last year. So the good thing about using ACE here is that we have a lot of root cause analysis that actually looks at repeated failure modes, and we want these to be accumulated over time. So we don't have to look at the same error pattern and do similar analysis over time, like repeatedly. So here, like AnyShift uses an architecture where ACE is basically running in the background to accumulate experience over time, to make sure that things are being like updated manually and autonomously, like we accumulate the insights over time. So the good thing is that they find that in production, this leads to 30% faster agents for root cause analysis in terms of time measurement. It also makes agent use tools more efficiently and results in fewer false leads and misidentifications of the errors or the root cause failures in production. So we're currently growing the ACE community beyond the paper itself, and we're really excited to see that the people using it in different ways. Yeah. And we also see a lot of additional work, more than just in the case for context, but also a lot of the related work we see is more related to continual learning and on reinforcement learning side. So the position we push out in this paper is that we want to treat context as a fast and test time medium for continual learning. So it's not a passive like a storage of things you have, but a proactive way you can achieve continual learning and a medium for that. And then our vision here is that in the long term, if you have knowledge you want to internalize, you can also distill selectively, like what you want to distill from the context into your weights. In fact, this is already happening. If you look at recent papers like Dr. Laura, people are already looking at how do you internalize context, internalize knowledge in the context so that they're more persistent. Yeah, and also things like agent skills and so on, make sure that we generate things that are more than just random text, but also things that are following like industry scale protocols. Yeah, so we also find a lot of opportunities in systems here. So for example, context learning as skill is one thing we're currently looking into. So we see an analogy between distributed deep learning and the context evolution as skill here. For example, in distributed deep learning, we have parameter servers, and in the case of data parallelism, we have different workers looking at different data. So each worker generates its own gradient, and then we do a gradient accumulation for one epoch of learning. And in the case of context evolution, we can also have a lot of agents looking at different data for each agent. And then we generate one context for each agent, and then we can accumulate these contexts together at scale to enable context evolution in parallel and more efficiently and a more diverse set of insights from different agents. Yeah. And another thing we mentioned earlier is how do we make sure that the playbook is periodically verified and cleaned up. So this is more like we want things to be stable and reliable in practice. Is there a way we can make things more verifiable in general? So one thing we explore right now is to generate agent skills, because agent skill is a much more like a formulated protocol, and it is relatively easier to verify or double check by some third-party checker as compared to a generated playbook. So that's something we're exploring as well. And eventually, we believe that a lot of everything should go into the model weights. Especially for frontier labs, we believe that consolidation of knowledge is an important part of learning. So here we're pushing out something during test time. But we believe that we should also close the loop by periodically stabilize and distill the knowledge in the context into the weights using methods like SFT or RLL here. But essentially, this is a kind of self-distillation. If you work on self-distillation, I think this is a big topic this year. So I think ACE is doing some kind of in-context self-distillation. We want to close the loop by doing consolidation as well. Yeah, and I want to finally talk about some of the community efforts we have. So here we quickly conclude what we introduced. We introduced context evolution as a new paradigm for AI adaptation. We introduced two limitations in existing work, brevity bias and context collapse. And to tackle them, we introduced a framework called Agentic Context Engineering, featuring recipes like incremental context update, itemized and bullet or sectionized playbook, and then this 3-agent autonomous loop for maintaining everything ordering. Yeah. And evaluation shows that we can enable self-improving agents during test time, and then self-improving domain AI with the ACE framework. And well, our current plan is that we want to make sure that ACE is more than just a paper. So we're growing it as a larger open source platform. So very, very excitingly, we're seeing a lot of people working on the ACE platform for follow-up papers. So for example, we are working extensively with researchers at Berkeley Skylab on a lot of follow-up evolving frameworks and benchmarking for a lot of these test time learning approaches. And the ACE like repo is we're developing is as a strong foundation for having a follow-up research projects. In fact, a lot of people are building on top of ACE. I have also been talking to people at the database group at MIT working on top of the ACE repo, because they're doing something on tool use. So we're trying to make this something that's a wider community effort, no matter if it's for research or for like industry use. So if you're interested in contributing or participating, you're very welcome to send me an email, or we're also having a quarterly roadmap where we have new features we want to achieve for this quarter, and then we have a Slack channel as well. So yeah, so that concludes my talk. I want to just thank everyone for joining, and I'll take any questions if you have, and if you have questions more than just a paper, I'm happy to take any of them. Yeah.
Cool. Yeah. Let's thanks Qizheng for. Any question?
So I have one question about like the agentic memory thing. So when you store the memory, say in the ACE playbook, have you observed like it how does it affect the performance of the agent? Where do you like from where do you inject the memory? Like further down the trajectory, does the agent like is the agent capable of like actually using whatever was injected properly or no? Or does it work better when it reads the previous like in the earlier stages of the trajectory?
So in the online case, we did some ablation study for like whether our like a way of introducing the playbook actually helps. So the short conclusion is that it helps because we are explicitly tracking which specific bullet points are used by the agent to, for example, solve the current task. And we do see many tasks that like are correctly solved with the playbook, but cannot be correctly solved without the playbook. Yeah, that is the short takeaway.
I think maybe just to kind of follow up on Mihir's question, because I think you also mentioned the mechanism, the deltas that you update. I think my question is, does the size of the delta in terms of the token count matter? So what I mean is ultimately it's a conditional probability distribution, right? If I'm making very, very small changes, I'm not assuming it even registers, right? I think the answer should not change if the system is working really well. Especially for if the context is already, if the playbook is already very long. I think I'm just trying to also understand, so position bias, I guess, was Mihir's question, is there a position bias? And I think my question is more sort of what is the smallest possible delta in terms of number of tokens before you actually see anything changing? If you have any opinion on it.
Got it. So the first question is whether we see things like lost in the middle type of phenomena, I guess. Whether it's better at using things at the front end or at the end. That is a good point. We actually did not look specifically into this. I would say it highly depends on the base model. Like if your base model has lost in the middle phenomenon, then sure, it's going to happen in the case of ACE as well. So the original motivation is we wanted to work with any large model if you have the playbook. So I think this depends highly on the base model. Yeah. And regarding the second question, what is the smallest delta? I would say this highly depends on your task. I can give you an extreme example. So let's say you have a very large distribution shift, like last hour you were working on math problem, this hour you work on coding problem. Then I have to say that your code book is entirely useless in this case. Then in this case, even minor updates on code related insights would help. So it depends on your data distribution, basically. That is my take.
Yeah, any other question? I also have a few follow-up questions, Qizheng. I wonder, I mean, since we are talking about agent memory, so there are many other ways to manage memory, right? You can use entity graph, for example. There are a lot of other works on agentic memory. So I wonder the way you manage memory, which is a playbook with delta update, how does it compare, or how does it differentiate, or how does it complement the existing methods for agentic memory management?
Yeah, I think that's a great point. So for example, if you look at existing frameworks like MEM0 or so on, I think a big part about existing agent memory frameworks, a large part is about memorization. So we take some static facts from users or etc. from during inference, and then we store that directly in the memory. So I think what we're trying to explore here is how are we able to extract the insights that are not available if you just store the static, for example, facts. For example, if you store the static trajectory from an agent, I'm pretty sure that is going to be very noisy. So and we find that an agent is not able to leverage such noisy information. So our framework, essentially, it is a way of condensing knowledge and putting them in a consolidated and compact way over time. So that is a short takeaway. If you look at like a lot of the existing framework, I think the spirit is very similar. The community has essentially converged on how we should approach the problem of managing memory. So for example, Manus has written blogs on, they believe that the incremental update is helpful. Last October or September, around the same time we push out the work. And if you look at OpenClaw, like people think that it's important to have a long-term memory and store potentially relevant things like in this daily log, like a second tier of memory. So I think the community has kind of converged right now. But when we were first designing this last June, I feel like most of work were focusing on a static storage scenario and static storage plus retrieval. So we want to, like, original motivation was we want to develop something that is much more condensed, and we want to make sure we don't just stop on a surface of storing static facts, but also procedural and contextual knowledge.
Got it. Yeah, thanks. I also have a quite minor technical question. So at the end of your talk, you mentioned this KV cache reuse, right? But I think actually this might be a pretty stupid question. But in my my understanding is even if you change a little bit of your like your context in the middle, but because first you have position embedding, and second your later token append to previous tokens. So even if you remove like a small number of tokens, the KV cache of tokens after the change you make, they're going to change, right? How can you reuse KV cache here?
And that's a great point. So this is something I did before this paper. So the short answer is that the numbers I show here is for the offline case. So the playbook does not change during inference. That's why we have 90% of the tokens unchanged. For the online case, we also experimented with like a KV cache, and the hit rate is like a 70%. So it's not as high because you change the playbook over time. But I think that's something that's during it's an active research actually. So if you read papers, like one work, if you follow work in the community, I think a lot of recent work is talking about position encoding independent storage of KV cache. Like you can store KV cache at any position and reuse them if that appears at a different location. So what is happening is actually like we are one work I did before the ACE paper is called a cache blend. So cache blend is a work that tells readers that we can store things independently from position encoding. Like if I have something at the front, and the next time it appears at the end, I can still reuse it, probably with some potential degradation in accuracy. So I think like this kind of new way of prompt caching is gonna be helpful in the near future. But at this point, like it still benefits from most of the tokens do not being changed from the last iteration. Yeah.
Got it. Thanks. Any other question?
So like one small question, like have you observed like how many times is the agent memory, whatever the context learned, is going against what was instructed in the system prompt? In some cases, like have you observed any cases like that?
So when you say going against, you are saying that things you observe during inference are like
by learning. So like maybe like while inference or learning. So say I have some instructions in some prompt or some fact written over there, and the agent over time learns something which kind of goes against or like is contradicting whatever is in my system prompt. So when you inject that later on in the trajectory, does the agent actually follow that or gives more attention to what is in your original prompt, like this?
Got it. So you're asking about contradicting information in the context. So the thing is that the system prompt we use is the simplest one from the React agent system prompt provided by the benchmark author. We didn't make like fancy changes to it. So it's very simple, and I don't see contradicting information to the system prompt. But if you're generally asking about what if we have contradicting information in the context, we did some noise measurement experiment for the paper. So our observation is that the ACE framework is able to tolerate some degree of noise. The only case we're unable to handle is that if you manually inject like a noise every iteration, like manually inject harmful information, then the system will fail. So otherwise, it has some tolerance to noise.
Yeah, my question was more like, say you are injecting the correct information, but the noise is present at the system level. So like you're trying to correct the trajectory later on by using the agent memory.
Oh, I see. I think this is a good point. Like people studying RAG as well. We have not observed this kind of approach in our. We haven't observed this in our experiments, but I have to say that this is a key issue that you want to address. Like how do you handle this? Like we haven't seen this in practice, but I'm pretty sure it might appear at some point if you have this kind of application.
Like we face this a lot while working on memory with the bench, because like some of the things are in the system ROM which kind of might be incorrect, and then we try to correct it later on, and agent does not follow the injected memory. Do you have an example? Like not
Oh, for 12 bench. I would give 12 bench a try for sure. Yeah, I think. I see. Yeah, I'll definitely take a look at this. I think it's highly dependent on your data. Yeah.
I think Dalbench also is like just really noisy overall. The guys had to even send some PRs to fix answers. So I think like it's one of those cases where the original instructions were just wrong for the environment in some cases, not everywhere. Hey, do you think I had it's not a question, I just wanted to get your opinion on some things, right? So like, because you've been working in the field of memory, and it kind of builds on the question that Hao was asking, which is so there are two things I wanted to kind of get. So one is, in the list of things that are moving us towards, and I won't talk about language model, but let's say agentic systems or just systems in general, to sort of this stateful, making these agents stateful and persist information and I think so. Definitely, memory is a very important piece. We have been thinking a little bit about, and this is purely thinking. There's no work here yet, but interactions of memory and KV cache, right? I mean, in some sense, like if you draw vague analogies to how human brain is organized in terms of short-term and long-term persistent memory, it's when the model is in session, your KV cache is, I mean, it's huge, and it works like this kind of an analog to a short-term memory. And what external memory has done is that it's because we've given it, like, when the session is over, or even during the session, it can write some or dump something into these stores. The only difference is that the two kind of memories don't share the format. They have very different, right? So if you think of KV cache and memory as memories, short-term and long-term memory, they just don't share a format. And I mean, you can draw any analogy. You can draw analogy to physical memory, so like RAM, and how swap files are used to then dump onto the disk when the RAM is too full, right? In a computer system, page files, whatever they're called these days. The one consistency there in these systems has always been that the format is the same, right? So you can move something in and out very quickly. So but the one thing that you have a bottleneck with, because most memories today are written in natural language, so the only way to kind of bring them back to the model is through the context, right? Like through actually telling the model again. I don't know, like, I just want, that's why I say it's not really a question. It's just a long-winded way of saying, what's your thought on, do you see a path from, loading memory one day directly into your or directly or algorithms that directly retrieve things back and forth between memory and KV cache?
Yeah, I think like this is related to the question we discussed on like any position KV caching. Like you want to make sure your KV cache is position independent. I actually feel like the more important agenda here is that for researching KV cache, can we explore things that KV cache can do beyond inference efficiency? That is actually a hugely underappreciated topic.
Yeah.
So I've been brainstorming this a lot with my co-authors at the Tensor Mesh. So what is happening now is that people treat the KV cache as something that's specifically used by inference engines to use prefill cost or maybe decode cost, whatever. So I think this is actually not the only use case for KV cache. There are a lot of things. Like there's a recent paper for iClear. They use KV cache for like reasoning and sampling, beyond just for like inference efficiency. And you probably like if you use like maybe if you have attention scores available, let's say maybe not KV cache, you can also use these as site information to determine like what is actually important in your context. So I think the important thing is whether we can find a way for KV cache to be useful beyond like inference itself, because all the memory work right now are on the application layer. It's pretty disjoint with things on the model layer. Like people working on infra do not talk a lot to people working on agents in general. I've done projects on both sides. I feel like there's a huge gap. It's very disjoint fields. So I think there needs to be something some way we can unify these layers later, because you want things to be efficient and loading context currently it's like standardized scenario you can handle it in inference engine, but the memory like paradigm is evolving very fast right now if you look at the agent layer.
I think that's been I guess this is the second part of the question, opinion, whichever way you want to phrase it. It's like so a lot of memory. Sorry, did you lose me?
Yeah, we lost you for a second. Can you repeat it?
Oh, sorry. I was just saying that the follow up on that one was like, and I think that this is kind of where I was also going in some sense is, or maybe not. I don't know. In some sense, the independent of KV cache or attention scores and the similarity with them, the format in which we save all our memories today, sort of natural language text. What's your opinion on that? I'll tell you mine first. I think it's very inefficient, and I think it's not necessarily like it's a great starting point, but probably not the most probably not the end, right? And I just wanted to hear like what's your take on it, what you're working on this problem of like how do you compress it? What are there better representations?
I think the main challenge is that for memory, like if you want to actually use it in practice, most people want a way to actually read what is in the memory. So you can always propose like human unreadable formats, no matter if it's latent space storage or like condensed representation. It's all possible. I just feel like eventually, if you want your memory to be interpretable or something you can manually check or verify, you have to convert it into natural language anyway. So, or another approach is to make the model think and remember natively in a different space. Let's say a latent space, or if you look at latest like a architecture like H4, is it H4 from CMU? I think like people are exploring with all these like storage and thinking formats. So, but I think a lot this might require changing the model architecture. So. Well, I would be happy to work on this kind of research if we have like at least one piece of GPU in our lab, but that's not like a trivial idea. I have to agree, it's gonna be happening sometime in the future, but in the short term, I think still gonna be text memory.
I completely agree with you that people would like to see what it is. I think my point is sort of like that doesn't have to be the final form in which the model consumes it, right?
Yeah, exactly. Yeah. So for example, on like there's an open source project, like they have this gibberish between like agents, like two language models communicate with some gibberish language, and that is I heard it's very efficient. So maybe that is one potential way we can use.
Cool. I guess if there's no more question, let's thank our speaker again. Cool. Yeah, I think we can end here. And thank you, Qizheng, again. Yeah, amazing work.
Yeah. Thanks so much for having me. If you're interested, please feel free to reach out. I'm also looking for a job this year, so yeah. Happy to chat about, like, if you're interested in contributing to the ACE framework, our community is growing right now. So yeah.
Cool. Yeah. And I mean, if you guys want to connect with Qizheng, I can also forward his information, contact information to you guys. Cool. Yeah. Thank you. And see you.
Yeah. Thank you so much for having me. Yeah.
Thank you. See you.
Yeah. See you.
Thank you.